review and talk about the atom in the periodic table. So let's make sure we get this down really quickly from grade 9 and 10 chemistry. What is the definition of matter? What does it mean if something is matter? Yeah. Occupies space, good. Very good. So occupies space and has mass. What else can you tell me about matter? Yeah, yeah, I like that. I'm not going to write that because that's encapsulated in this, though it's totally true. What is matter made of in our universe? Atoms, that's right. So made of atoms. I mean, the other thing we can say, these atoms, we can even be a little bit more specific. If you remember, do you remember talking about the kinetic molecular theory of matter? KMT? Should have talked about a lot in grade 9 and 10 science. Okay, well, we're going to talk about it now. The kinetic molecular theory of matter basically says that everything's made up of particles. We call them atoms or molecules. But that these are always in bless you. These are always in motion. Yeah, they're always in motion. They're always moving. All matter always has some kinetic energy to it. It's always in motion. By the way, we can measure this motion. If we touch an object and its particles are moving very quickly, what will we observe about that matter? How will it be perceived by us? All those particles bouncing around, they're moving real fast. And if you touch them, they're going to bounce into your particles and make them move around fast. And we would feel that. Our senses would detect that as? Energy. Yeah, what kind of energy? Kinetic. Specific type. This is heat energy. All it means for something to be hot is that the particles that it's made of are moving around really, really quickly. Very good. Have you heard that before? Is that something you've talked about? Ah, interesting. Well, that's okay. We're going to learn lots about it now. So heat energy, and specifically we can say, actually we could say this. We could say fast-moving particles, we define that as hot. And slowly moving particles we define as cold. And of course, these particles never stop. They can't be completely without energy. It doesn't work that way. There's a lower limit to heat. In theory, things can get hotter and hotter and hotter. There's no upper limit to how much kinetic energy you can give particles, but there is a lower limit. They can't stop moving completely. If they did, it'd stop being mass. So these are always in motion. The other thing about atoms, I mean, we are tricked by our eyes and the fact that there's lots of atoms in you. But of course, we know that when I touch this desk, no two things are physically touching at all, right? The negative charge of the electrons in my hand and the negative charge of the electrons in the desk are repelling one another, and it puts force up against me. But I'm not actually solid, am I? I am, in fact, mostly... Yeah, but even go smaller. I'm mostly what? I mean, I'm made of atoms, and an atom is mostly small. Yeah, they're really, really small. And not just are they small, you have a small nucleus, and then way out far away from it, you have smaller still electrons. I am mostly empty space. I'm mostly empty space. And atoms are basically nature's building blocks, or nature's Lego, really, which is to say we can take atoms and we can put them together. When we put two atoms together, what do we make? Or more than two? Yeah, it could be a molecule if it's covalent, for sure. Or it could be an ionic, what's the word? Molecular blank, ionic blank. Very good. They can be combined to form compounds. Now, with all this in mind, atoms themselves in grade 9, you should have learned about their composition and what they're made up of. So who can tell me about atoms? Yeah, they're very tiny, definitely. The atom itself is composed of 3 smaller subatomic particles. Subatomic literally means smaller than the atom. I'm not going to bother writing that. But what are the 3 subatomic particles? The 3 particles that atoms are made of?
Protons, neutrons, and electrons.
Very good. We have protons. We have neutrons. And we have electrons. All right. What charge does a proton have? Positive, good. And in fact, we define it numerically. We say that the proton's charge is +1. Makes sense if you think about it. If you're going to define a unit of charge, why not just say it's whatever this has, that's 1. So a proton has a positive charge. What about a neutron? Yeah, which means what? It has, yeah, no charge at all. Very good. And electrons. Yeah, they have a -1 charge. Sorry, I'll get out of your way. What about mass? What's the proton weigh? I mean, I'm not going to ask you in grams because the number would be very, very what? Very small, right? Protons are very, 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 very small. It'd be, if you measure it in kilograms, it's a decimal with about 25 zeros before you get to a number. So we're talking small. But do you remember we define its mass as 1? Does anyone remember? What's that stand for? Does anyone remember? I promise you learned it. I promise. One atomic mass unit. All right. Again, it's a clever unit. The atomic mass unit is the mass of 1 proton. What does a neutron weigh? Anyone remember? Oh, what's a negative mass? Does anyone remember? Is it smaller? Yeah, the neutron is actually also one of the heavy particles. The neutron is roughly the same mass as the proton. It's actually a little bit heavier, but it is essentially the same if you round to the nearest atomic mass unit. Now, the electron, on the other hand, is not massive. If you remember when the electron was first discovered with Crookes tube, J.J. Thomson using Crookes tube and the magnet. Have you ever seen that? And the stream of particles deflected. Did you guys see that? No? Ooh, we might have to dig that one out for you if we have time. Anyway, Thomson proved that there was this negatively charged particle called the electron, and it was very, very, very light. It is very low mass. In fact, rounded to the nearest atomic mass unit, it essentially weighs 0 atomic mass units. Now keep in mind, that doesn't mean it has no mass. It just means it is way smaller than these guys. Does that make sense? It's like how the air in the room doesn't affect the scale, your bathroom scale, right? It's not that the air weighs nothing. It doesn't. Air has mass. It's just that it's very light. Does that make sense? Likewise, electrons don't weigh nothing, but they weigh next to nothing compared to these guys. Does that kind of make sense? Mm-hmm. Last thing. Where do you find these? And if you think about it, this tells you everything you need to know where you're going to find them. Think of our solar system. What is the big heavy object in our solar system? Not the solar system. Our galaxy, yeah, they postulate that there's a black hole in the center. But in our solar system, the big heavy object is the sun. The sun. The star at the center of our solar system, we call it the sun. And In our solar system, the sun accounts for, rounded to the nearest percent, 100% of the mass in our solar system. The overwhelming majority of all the weight in our solar system is in the sun. Does that make sense? Likewise, and that's right in the center, and it's the part that everything revolves around. Likewise, what makes up the center of the atom here? Yeah, we call it the nucleus. And what do we find there? We find all the big, heavy, chunky stuff. So it's where we're going to find protons and where we're going to find neutrons. So these are found in the nucleus. Now, if the protons and the neutrons behave like our star in our solar system, the big central mass around things which orbit, what do the electrons behave like? Yeah, they behave like the planets, which is to say they are found. Very good. They orbit the nucleus. Now, I want to talk briefly, and we're not going to talk too much about this, but in grade 9 and a bit in grade 10, you should have talked about the difference between pure substances and mixtures. Does that ring a bell? What is a pure substance? Anyone? Yeah, all the elements are pure for sure. So if it's just one atom, so anything made from only one type of atom, for sure. And we call these elements, right? So for example, what's an example of an element? Something that you could have, maybe you have it. Oxygen, gas in the air is an element. What else?
Calcium.
Yeah, pure calcium. I have some calcium metal in the back. We have to keep it immersed in oil because it's actually pretty reactive. On the other hand, something that isn't reactive is like copper, right? The copper pipes that you have in the wall, they're actually pretty much pure copper. The only type of atom in them are copper atoms. But it doesn't just have to be, that's not the only thing that's a pure substance, because it could also be anything made from only one compound. And remember, a compound is atoms stuck together in a specific arrangement. What's the classic example of a compound?
Water.
Yeah, water, right? Good example is water, which is one oxygen bound to two hydrogens at an angle of, geez, I'm trying to remember, I think about 109.8 degrees. There it is. Right? So you're a pure substance if all of the particles that you're made up are the same, whether they happen to be just an atom or it could be a compound. Right? Carbon dioxide is two different elements. It's carbon and it's oxygen, but it's still a pure substance because carbon dioxide is stuck together in that specific arrangement. Does that make sense? Cool. On the other hand, then, what is a mixture?
Made of two or more.
That's right. You should have in 9 and especially 10 chemistry talked a fair bit about like the different types of mixtures. Can anyone remind me what the types of mixtures are? Mechanical mixtures, what's that mean? From a mechanical mixture is sometimes also called a heterogeneous mixture. Does that ring a bell? So let me give you an example. If we wanted to go, you don't have to draw this, but you could if you feel like being artsy like me. If we want a pure substance, we could have, ignore the beaker itself, we could have water. That's a pure substance, right? That makes sense? Now, I could also have this, and it could be salt water, which means it's H2O, but it's also, does anyone remember the formula for common table salt? Very good. Now, in this case, can I, if it's a relatively light salt mixture, can I tell the difference between these by looking at them? No, they look identical. So this is a pure substance, and this is a kind of mixture that is specific. We call it a solution, which is sometimes also called a homogeneous or homogeneous mixture. Homogeneous means, genus means like what we're able to see or experience. Homo means one, right? Right? So homogeneous means that it all appears in one way, right? Whereas the other type of mixture, I could have this, and I could have the water, and I could have some rusty nails. Mr. Orlando's patented nail water. It cures what ails you. It's copyright, by the way, so don't try to make it yourself. Here we have a mixture. I've mixed two things together, specifically water and rusty nails, but we can see the different parts, so we would call this a mechanical mixture. And the other term we'll sometimes use is we say this isn't homogeneous, it is heterogeneous.
Can I advertise for Semi, please?
Yeah, quickly.
Okay. You can talk about it. Oh.
Quickly. Got to be honest, that's not a good start to quickly. Carry on.
So we're advertising for Semi, and we're just wondering how many people are interested in going.
Did you buy a ticket, Kayla?
There you go.
Well, look at the numbers.
I believe I'm going to supervise, I've been told, so.
Okay, yeah.
Yeah.
I'm supposed to come because I'm missing
Tickets
the
are
concert.
$10. It's gonna be a great time. It's red carpet themed. I could say so much more, but I really feel bad for interrupting this chemistry class.
Okay, that's all, guys. Thank you for your time.
We love you.
Bye. Bye.
Okay, I made a short list of the reasons you should go. You should go because it's only $10, because it's a great time for purposes of guilt. Red carpet themed, kazoo question mark, and what was the last one? Ah, food included. These are good reasons. Okay, there you go.
Lastly, Eastdale.
This is Eastdale.
Eastdale is cool, right?
Potential romance question mark? I don't know. So anyway, no, don't talk to me. I don't like any of you. All right, so there we go. All right, so that's a little sidebar, and I just mention it because that's some grade 9 chemistry that's going to come up a lot. Now here we go. I have got, for your viewing pleasure, the periodic table. In fact, I've got one entry from the periodic table, aluminum. All right, so let's talk about this. Obviously, this is, I'm going to get really technical here. Aluminum is this thing's name. Yes, that's its name. Now, there's something I don't like. which is they show it in capitals here just for kind of typographic reasons. But I want to be clear. Look at me. If you use this in a sentence, it should actually be lowercase. Listen, aluminum isn't a person, and you're not going to hurt his or her feelings by putting it lowercase. Chemicals actually have lowercase names. Despite what the periodic table may say, and yours has every single one capitalized, that's fine for a periodic table. But if you're using the word aluminum in a sentence, it is not capitalized. And yes, I will yell at you if you capitalize it. So don't. All right?
Okay.
They're not people. They're elements.
They're things.
Okay. Now, what do we call this? Very good. The chemical symbol. What rules do we know about the chemical symbol? Yeah, the first is uppercase. And if there is a second, it's lowercase. Very good. If you put two uppercase letters next to each other and it's supposed to be this, I'll throw things at you. I won't actually throw things at you because that'd be inappropriate, but you know what I mean. I'll be unimpressed. All right, first letter is uppercase, second letter is lowercase. Most of them are intuitive, some are not. If you're really good at Latin, all of them are intuitive. Right, but like sodium, what's sodium? Weird, right? Comes from natrium. It's the Latin for salt. Or for sodium metal, actually, sorry. Iron, what's it? Fe comes from ferrous, Latin for iron. Gold. Yeah, it's Latin for gold is aura, right? So if your Latin is strong, but most of these are intuitive. Now listen, I don't make you memorize the periodic table. You will absolutely memorize the parts of it we use a lot, and we're going to use parts of it a lot. But at no point do you have to sit down and study this thing as if you need to remember the first 20 elements or anything. I think that's nonsense. We're not
That's
doing
what they made it. Well, high school do in grade 9.
Probably a better or worse teacher than me. I'm not sure which. You can
That's what
decide.
color it is.
But I think that's wasted time. And I promise the important bits you will more than have memorized by the end. Now, what is this here? The atomic number. What does it tell us? Very good. So it tells you the number of protons for sure. So from this, we learned the number of protons. Now, that is the very definition of an atom. By which I mean this. If you look at your periodic table, aluminum, for example, has an atomic number of 13. That means anywhere in the universe you come across an atom with 13 protons, it is aluminum. The other things are variable. Aluminum can lose electrons, still aluminum. It can gain electrons, it's still aluminum. You'll find aluminum with more neutrons, still aluminum. You'll find aluminum with less neutrons, still aluminum. But by definition, the definition of aluminum is any atom that has 13 protons. This atomic number is what defines which element an atom is.
Isn't protons equal to electrons?
Well, very good. This is what we're going to talk about. Now, in a neutral atom, in an atom that doesn't have a charge, if there are 13 positive charges, there must also be
13
negative charges. So in normal situations, when it's a non-charged atom, whatever the number of protons is, it should also be very good. It's also the number of electrons in a neutral atom. In a neutral atom. And again, most matter is electrically neutral, right? When you walk around and touch things, it doesn't electrically shock you. It doesn't have a charge. Most things are electrically neutral unless we give them extra electrons or take electrons away. Does that make sense?
Mm-hmm.
All right. Now that takes care of everything, and that's everything I need to know about the last number. And this is what? Very good. This is the mass number, sometimes called the atomic mass, sometimes called the atomic weight. That's not a great description. Mass is a better description. Now, remind me, what are the two heavy parts of an atom? Protons and neutrons. How much do they weigh each? One. So together, they're going to add up to this. Now, tomorrow, Tuesday, we're going to talk about why this isn't 27 exactly. It's an average. This is the average atomic mass. So it's the average mass of an atom. Why is it useful? I mean, it's interesting, I suppose, but specifically if we're talking about the model of the atom, not electrons. We know the number of electrons. Very good. We can use it to find the number of neutrons. How do we do so? How do we do so? How does this tell me the number of neutrons? Yeah, good. If the only two things that weigh anything are protons and neutrons, by the way, if you went off the page, I advise you just, highlight it and move it over. Just like that. If the only two things that have mass are the protons, and we have 13 of them, we can figure out how many neutrons there are by doing subtraction. And round this. Work with round numbers. 26.982 is essentially what? 27. And if the whole thing weighs 27, and 13 of that comes from protons, how many neutrons do we have? Very good. Does that make sense? Tell me if it doesn't. So 27 minus 13 equals 14. That's the number of neutrons. Does that make sense? Really quickly, let's look at, may I? I don't know. Let's look at cobalt. And I want you to tell me everything I would want to know about cobalt. All right, so go ahead and do that. What do you got? What do you got? Okay. Yeah, Ms. Gauthier, what do you got?
27 protons, 27 electrons.
Okay, I'm going to pause you there just for a moment. Okay, so we're being told 27 protons, 27 electrons. How do we get that? Yeah, how do you get that? Good. So the atomic number tells you how many protons, how many electrons, but how many neutrons? Okay, how do we get that?
Are you sure you're math, please? Need extra people.
Very good. So if the whole thing weighs 59 atomic mass units and only has 27 protons, the difference, that 32 remaining atomic mass units, must be provided by 32 neutrons in it. Again, why is that rounded and not a perfect number? Because it's an average. And we'll talk about that tomorrow. Some cobalt actually has a few more neutrons. Some actually has a few less rather. We'll talk about that. Maybe I'll talk about tomorrow. Anything to avoid a staff meeting, right?
What are we going to do if each 2 days in a row? Then?
Oh, my goodness. Yeah, no. All right, now, let's remind ourselves then that the orbital model of the atom is the one that you've learned so far. Why do we call it a model of the atom? What does that mean?
Or
What does it mean? So what do I mean by orbital? When we talk about the orbital model, what is doing the orbiting in this model?
Electrons.
The electrons, good. Why do we call it a model? Because, listen, the orbital model of the electron is to an, of the atom rather, is to an atom like a map is to a city. When you look at a city map, you see this very simplified document, right? That has straight lines on it and shows where things are, but it's just a simplification of the real thing, right? It tells you roughly where things are. It's useful for getting around, but it's not a real city. It's not how the city actually looks. When you go out there, there aren't words written on each street saying what they are, and they aren't perfectly bright yellow colored, right? Does that make sense? And walk around, though you're not going to see the big like red little spotty thing that Google puts on stuff, right? Because it's just a model. It's just a way of showing how a city works. Likewise, if you take grade 11, or if you take grade 12 university chemistry after this, you're going to learn a more complex model of the atom, something called the quantum model of the atom. And it is a more full, more complete map of how the atom looks. But in our basic model, what lies at the center of an atom? Anyone? The nucleus. Good. So there we are. And in the nucleus, what do we find? We find protons and we find neutrons. And there they be. Now, where do we find the electrons? Well, we said we find them in
Orbit.
I don't love that. You know, my grade 9 science teacher made us use a compass to do these. I kind of like that, actually. So these are electron orbitals. And do electrons just go wherever they want? They just kind of cram in and they jockey for position and this or that? Yeah, the first orbital actually will only hold a very specific number of electrons. It will hold 2. How many are held in the second shell? Ooh, we have disagreement. I suggest that you guys wrestle, and whoever wins, I wasn't done yet. Fine, it's 8. Spoil my fun.
That's why I was first.
To spoil my fun?
Yep.
I don't believe it. All right, now I want to look at the periodic table because the periodic table is very carefully set up. And I'm sure you guys talked about this a lot, and I'm sure I'm not telling you anything new when we look at this. But the periodic table is designed to show us information about the atom just by glancing at it. So let's look here. I have put here the first bunch of rows. Now, this would be what? Good. This would be what? Okay, now, how many electrons does hydrogen have? 1. And so that would just go in the first shell. How many electrons does helium have? And that would fill up the first shell, right? Now, by the time we get to, what is this? Lithium. Good. By the time we get to lithium, it has how many electrons? 3. The first one would go in the first shell. The second one would go in the first shell. But now that first shell is full, which means its third electron is going to have to go in a new shell, into a second shell. Does that make sense? So if we look here, everything in this row, hydrogen and helium, has how many shells? 1. Now we said the second shell holds how many electrons? How many? 8, right? That's what you told me. Prematurely, might I add, but that's okay. Well, let's keep in mind that lithium will have how many electrons to put in that shell? Well, but how many in the outer shell? Just 1, right? And then magnesium will have 2. And then aluminum will have 3, silicon, phosphorus, oxygen.
What do we?
Oh, I'm on the wrong order. Boron, carbon, nitrogen, oxygen, fluorine, and then neon. And by the time we get to neon, it has 8 electrons and that shell will be full. So everything in this row will be a full first shell and then starting to fill up and eventually filling a second shell. Which means that when we get to the third shell, that's all of the elements here in the third row. By the way, how many electrons fit in that third shell? Yeah, and look, 1, 2, 3, 4, 5, 6, 7, 8. Ah. 3 shells. My God, it's like somebody planned this thing right out. And then after we get to, yeah. No, it's all taken. Thank you, my friend. And then when we get to this shell, or this row, these all have 4 shells. By the way, the 4th shell, how many electrons does it hold? Try again. Not 16.
18.
18 is good. So if you remember, the first shell holds 2, then 8, then 8, then 18, then 18 again, and then lots. 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and 32. And that covers all of the elements that have ever existed in the universe that we know of.
We forgot the element of surprise.
Moving on. So here's the nice thing. Just glancing at the periodic table, we can know how many shells an atom has. Really quickly, strontium, how many shells?
5.
Take a look, you got the periodic table in front of you, right? I gave everyone one, is that true? 5, how did you know that? Well, let's take a little look-a-roo, shall we? Strontium, chemical symbol SR, is in the 1, 2, 3, 4, 5th row. That means it's got 5 shells. What about phosphorus? How many shells does phosphorus have? 3. And again, we know that because if we look at phosphorus, where it's number 15, it's in the 1st, 2nd, 3rd row. So the fact that it's in the 3rd row means that its atoms have 3 shells. It's nice. I don't have to count electrons. I don't have to go like, okay, the first 2 fit in the 1st shell. That means I have 11 left, 8 fit. You know what I mean? You don't have to do any of that. You can just look at the table and it is telling you how this atom works. Now, the other thing we might want to know about is not just how many shells it has, but say phosphorus. It has 3 shells. The first shell is going to be
2.
and it's going to be full, right?
Yep.
The second shell is going to be
8.
and it's going to be
Full.
full. The only one we have to ask about is, yeah, the final shell, whatever that final shell may be. That's the one that might not be full. In fact, it probably isn't. So let's look at not phosphorus because it's not on my, what did I just do? Oh, I hit the new page button. Oh, phosphorus is on here. We're good. In fact, phosphorus lives right here, right? Okay, so let's look at it then. How many electrons does it have in its outer shell? Well, we could do this by knowing, okay, phosphorus has 15 electrons, right? How many go in the first shell?
2.
So that's 13 left. How many go in the next shell?
8.
And 13 minus 8 is 5.
5.
And so there's 5. But do I have to do that? No, because the periodic table is set up such that I can do what to figure out how many electrons it has? Count. I just count over. 1, 2, 3, 4, 5. Does that make sense? So if we look at phosphorus, we know that it has 3 shells and 5 electrons in its outer shell. And we know that without even looking at the numbers, just by looking at its blank location on the periodic table. Does that make sense? What about, oh, I don't know. What about this fellow here? What is this and what can you tell me about it? Yeah, I believe you. Okay, what can you tell me about zinc? Just looking at it. No numbers, just its location. What do we know?
4 shells.
Okay, good. It's got 4 orbitals, 4 shells. What else can you tell me about? Very good. It's got 12 electrons in its outer shell. Very good. Does that make sense? That should be review, I hope. Did everyone learn to read the periodic table that way last year? If not, that's okay, we'll talk. But reading the periodic table just visually is a really important skill. And I have to say, like, I think we do a much better job teaching this now than when I was in high school. I remember finally kind of figuring this out, like partway through university and being like, oh my God, the information is all right there. So yeah, and you guys had what? You had Pitchell last year?
No.
Not you, but everyone else had Pitchell last year for chemistry? Who did you had Trush?
No.
You not me, did you? No, you didn't have me.
I have Paul.
You had who?
Paul.
Oh, right. Okay. Was that 2 years ago?
Yes.
Right. That makes sense. Okay. Now, knowing this, we can make a Bohr-Rutherford diagram. Let's start with aluminum. All right. Aluminum has how many shells? Okay, so 3 shells. And how many electrons in its outer shell?
3.
Okay. What's a Bohr-Rutherford diagram look like again? Well, we draw our beautiful nucleus. I said we draw our beautiful nucleus. There we go. And then in this case, how many orbitals am I going to make again?
3.
Oh, well, that didn't go well. That didn't go well at all. Quiet. There we go. Now, the nice thing, if we're drawing a Bohr-Rutherford diagram this way, is we know the first shell is going to be,
2.
yeah, we know it's going to be full, right? And it holds 2. What about the second shell? 8. Now, you will find different conventions. Some people put them equidistant. Oh, that's not where those go at all. Let's try this again, shall we? I am a big believer in pairing them off at the compass corners. And we'll talk more about why that is if you take grade 12 university chem. But electrons like to live in pairs. So I kind of like that. And then how many fit in its outer shell? 3. Good. 1, 2, 3. And this is one thing that is important. They should get 1 to kind of each corner first before you double up on any. That's the usual convention in how we draw them. All right, and then what do I have to write in the middle here? Protons. Good. How many protons does aluminum have?
13.
Good. And how many neutrons? Yeah. Which we figured out earlier, right? Okay, there we go. Now, a Bohr-Rutherford diagram is a good representation of what an atom kind of looks like. We're probably never going to draw one again. Why? No, just because they take too long. I like making people do work. It makes me feel powerful. But one of the reasons I don't like them is they contain a lot of useless information. And this is one thing I want you to know. Chemistry is all about chemical reactions are all about the behavior of electrons in the outer shell. That's where chemistry happens. By the way, what do we call the outer shell? What's its name? Somebody said? Very good. We call it the valence shell. So chemistry is all about behavior of these electrons in the outer shell, which means in this whole diagram, are protons involved in chemical reactions? No. No, protons stay put. Are neutrons involved in chemical reactions? No, because where do we find both those things in an atom? In the nucleus. In fact, if these do react, what kind of reaction do we call that? Not a chemical reaction.
Atomic reaction.
Yeah, in fact, there's a more appropriate name for it.
Luleal.
A nuclear reaction, right? When protons and neutrons are involved, that is no longer chemistry, that is nuclear reactions. That's nuclear physics at play. Chemistry isn't about those. Chemistry is about this guy right here, the valence shell electrons. So what do we call it when I draw a diagram like this, but excluding all the protons, excluding all the neutrons, and excluding all the electrons that are buried in the lower shells? Yeah, we call it a Lewis structure. Sometimes you'll see the term Lewis dot diagram. I don't love that term. But sometimes they call it that. I will typically call it a Lewis structure or a Lewis diagram. So here's the nice thing. In a Lewis diagram, all we care about is valence electrons. So let's talk magnesium. What am I going to put in the middle? I'm not going to put protons and neutrons. I don't care about them. Yeah, I'm just going to put the chemical symbol. And what am I going to round it? The electrons. Now, magnesium, let's go back to our periodic table. Where is it found? In this lovely fellow. Yeah, in fact, it should be this one, right?
Yeah.
Is that it? Okay. So if that's magnesium, what can you tell me about it? Well, first of all, you can tell me something I don't care about, but what would that be? It has 3 shells. We know that, right? But what shell do I care about?
Last one.
The last one, that 3rd shell, that valence shell. By the way, what will be a full shell for it? It doesn't have a full shell, but that shell holds how many? 8. Does it have 8? No, what does it have? 2, right? We just count over. Just count over. If it were here, it would have 1. If it's in the 2nd spot, it means it's going to have 2. Does that make sense? Okay. So we can look here and we can already say 3 shells, 2 electrons in the outer shell. And it's those 2 electrons in the outer shell that I actually care about. And here's the rule. They go on the compass points, okay? Northeast, southwest. You will choose which compass points you put them on conditionally. You know this, right? When you're making ionic compounds, sometimes it makes a lot more sense to have the empty space in one spot than another, right? They go on the compass points, though, and every compass point gets 1 electron, and then they double up. Does that make sense?
Mm-hmm.
That's going to be important. Listen to me. If you give me this, I'm going to give you this. All right, I want nice, clean looking. Now there's an exception to that, which is what is the only element that has 2 electrons, but that makes for a full shell? Helium. So we would actually draw helium like this because they are paired up. But that would be the only exception. Even then, you could kind of put them wherever was most appropriate. That won't come up because helium is what kind of gas? Noble gas, and they don't react. They can under extreme conditions, but under typical conditions, they will be non-reactive. Yes. Okay. What about aluminum? What is it going to look like? What's its symbol? And how many electrons in aluminum's outer shell? So where should I put them? Yeah, and again, you have some freedom as to which compass points you pick, but we want them filled out thusly. What about argon? Yar. AR. This is where, if I were of that disposition, I would ask you what a pirate's favorite noble gas is. Arg. But I'm not going to, because then I wouldn't be able to respect myself. All right. Argon, what is its electron configuration? It has 8, which tells us what about it?
You can fill up all the other shells.
Yeah.
Right.
Sorry?
Isn't it stable?
Very stable. Yeah. You can think of that element and this is only an analogy, this isn't the actual description, but you can think of it kind of like, your tires spinning on your car, which is if they have an unequal weight distribution. You ever driven a car that has unbalanced tires? Funk, 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 right? You feel every rotation of the tire. Whereas if they're properly balanced, nice and smooth, right? That's only an analogy, by the way. It's not quite that simple. I don't want to imply that elements are like tires because they're not. And what's the last one I asked for? Chlorine. And what's chlorine look like? 7. So how many electrons should it have? 7. So 1, 2, 3, 4, 5, 6.
7.
And then a lonely little remaining spot where an electron wants to be, but isn't. Very good. I'm going to separate these thusly. And I might even put titles. Oh, and I just did it. See, it's always tempting to put things in capitals. But again, these aren't people. These aren't their names. And they should be lowercase. If you find me putting them uppercase, please yell at me. By the way, when I say yell at me, I don't actually mean yell at me, be polite, but you get it. There we go. Now, listen. Being able to reliably draw a Lewis diagram from the periodic table is really important. There's a reason we actually gave you a day to review it right now. That's because you're going to draw a Lewis diagram probably 15 times a day between now and the end of this course, every day. All right, we're going to do it a lot, which means you need to know it. This isn't something you can forget. It's not something you can breeze by. If you don't understand it, nothing wrong with that. Come talk to me. But make sure you understand it. Make sure you can look at the periodic table and know how many valence electrons something has. Look at me. 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 Okay, listen. Make sure you can look at the periodic table and know what its electron configuration is going to be, because that's important. Okay? I promise. You're going to have to know it. The flip side to this is this, and I know I've said this before, but you're going to love this course, A, because I'm here, B, because all of you are here, C, because chemistry is fun, but D, because chemistry is the most straightforward of all the sciences by far, by a country mile. It's not tricky. That doesn't mean it's not hard. It doesn't mean it won't be difficult at times. It doesn't mean you won't have to work at it. But here's what it's not. It's not all over the place. We're going to learn a skill. You're going to use it every day for the rest of the course. And the day after that, you're going to learn a new skill. It doesn't replace the old one. It just means that every day for the rest of the course, you're going to have to do both of those things. Does that make sense? Yeah, but even more so than math. Because math, it's like, hey, today we're talking about parabolas. Tomorrow, geometry. Day after that, like unit conversions. You know what I mean? Chemistry, none of that. Everything you use, you're going to use every day. There are honestly about 3 lessons that aren't like that in the whole course. And that's the only stuff you're going to find yourself studying for on the exam. I promise. The rest of the stuff you don't need to study. By the time you get to the exam, you're like, I do this every day. I breathe this. Right? And that's what's nice about it. Your homework for today. All right. If you haven't already, be sure to finish your Getting to Know You survey. You're losing 5% a day at this point. That's dumb. You can get perfect on this. So get perfect. I will start taking marks off if I don't have it by tomorrow. All right? So log on to Teams, get on there, get this thing filled out. I will be deeply ashamed of you if you get less than perfect on that. The warning is out there. I haven't mentioned it. I should have put it in here, but also science safety. Get it done. About half of you are done. All of you need to be done. If I have to hold up the first lab because you haven't done your science safety training, I will freak out. You'll watch me have a straight up hissy fit. More to the point, you'll be holding everybody back from doing fun stuff. So don't do that. If you remember, I asked you to design a little experiment. Yes? Well, don't forget. Get it done. I'll tell you about, you're going to design a very simple little experiment. It can be about anything you want, like literally anything. It just has to have an independent variable, a dependent variable, and some quantitative measurement to it. You need to get that done. We were going to have a couple of class days kind of dedicated to it. We're not now. What I'm going to do is we're going to stretch it out to about a week. And at the end of class, I'm going to talk briefly about it, okay? But at a bare minimum, listen, look at me. At a bare minimum, by Tuesday, I need you to have checked your experiment with me. And by Tuesday night, like by the time we get back on Wednesday, you need to have actually done your experiment and collected data. Not a bad idea to run your experiment by me before leaving today, but you can also message me on Teams, all right? But I want you to get going on that, all right? Nothing's due with that yet, so you're not late, you're not behind, but you will have trouble getting it in on time if you don't have that much done. Does that make sense? So you need to run your experiment by me and collect your data by Wednesday, because on Wednesday we're going to do something with it, all right? Then I want you to draw me, pick 5 things on the periodic table, draw Bohr-Rutherford and Lewis diagrams for them, and finally complete these Bohr-Rutherford diagrams down here below. I want to know how many protons, how many neutrons, and tell me what they are. Also, you can point out what I don't like about them. These are from the internet, but what don't I like about these? Don't tell me now, just, you know. Quiet you.
Hush. Is there anything you do like about
Hint.
it?
It's Sam. I don't like Sam. All right.
That's okay, I don't like it either.
All right, I'll be quiet. There you go, guys. And if you're not sure what's going on with that experimental bit, come talk to me and we can hash it out.